Hello everybody and thank you for watching this video. Today I'm going to explain some basic probability distributions, what are they modeling, and what are the connections between them. First of all, what is a probability distribution? Probability distribution can be taken very literally. It is a distribution of a probability mass over some interval of a real line. So let's look at the example. This first example is a uniform distribution. Uniform distribution means that the probability mass is distributed uniformly on an interval from A to B. That means that any value in the interval from A to B is equally likely. Where do we see such distribution? For example, if you look at the wind bind and if you want to see the angle of this bind at any specific moment, then most probably it is reasonable to assume that all angles are equally likely, and then the distribution of the position of the angle of the wind bind will be somewhere on the will be uniformly distributed on the interval from 0 to 2 pi, so from 0 to 360 degrees. So in any basic statistics course, this is the most important distribution, the normal distribution. What does normal distribution tells us? If we look at the density here, then we see that probability mass is distributed differently here. It is very much focused around the value mu, around the average. And then further we go from the average, less likely we see the data that is so far away. An example of this is something that has some typical value. For example, we can think about a power of a motor, and if there's identical motors produced in an identical way, then the power also should be identical. But in real life, it will not be exactly identical. There will be some random fluctuations, and then this power of the motor can be modeled very well with a normal distribution. There are many other examples. For example, people's height, people IQ, any measurement, physical measurements could be modeled very well by normal distribution. Every time apply normal distribution, you have to ask yourself, is there such typical central value around which the rest is distributed, and further we go from it, less likely it becomes. Sigma here is a standard deviation, and basically it is very unlikely for this value to be beyond the interval mu plus minus 3 sigma. That is also where lean 6 sigma comes from. Mu plus minus 3 sigma basically covers for entire randomness in a normal distribution. Next distribution is a different model. It is an exponential distribution, and as we see, the probability mass also is distributed differently. It is likely, more likely outcomes are around 0, and then the probability decreases exponentially. Therefore, the word exponential distribution. With parameter lambda in the exponent. So what does that mean? So this model is used, for example, for times between phone calls in a call center, but can also be used for modeling time to the failure of an equipment when this equipment is as good as new. If equipment is as good as new, then its failure is a purely random process. It can fail any second, basically. And it doesn't matter if the equipment is as good as new, then okay, if new equipment starts working and say after 1 day, after 2 days, after 3 days, it is basically as good as new. So the probability of it to fail remains the same at all these moments. And that is what is called the memory-less property of exponential distribution. And if you compute the probability of failure in this particular moment, then it will follow exponential distribution. So also this call center example, we'll come back to it. Okay, next very important distribution, and I put it next to normal because it is also one of the central distribution in any basic statistic course, is a binomial distribution. It is a discrete distribution. Why? Because probability mass now is concentrated on discrete values, 0, 1, 2, 3, etc. So binomial distribution is a model when we have n independent experiments, and each experiment can be successful or not with probability p. For example, we have here this signals on a rail line, and the signals have these lumps, and these lumps, for example, can be defective. So if we have n lumps and each of them can be defective with probability p, then the number of defective lumps will be binomially distributed. It will be some random number. It can be 0, it can be 1 or 2 or 3, etc. We don't know how many defective lumps are there. It's random, but the probability distribution is binomial with parameters n, p. And as we see, if we look at the plot here, then the height of a bar corresponds to the probability, and it is natural that most likely values are around average, so around np, so fraction p of the lumps is defective, so average number of defective lumps is np, and that will be also the most likely values. And then the values further from that will be a little bit less likely. So this is a binomial distribution. And finally, another important distribution that we studied is the Poisson distribution. And I used exactly the same lambda and exactly the same icon for the call center intentionally. So what is the Poisson distribution? If you now look at a call center, then the number of calls arriving, say, per hour or per minute, depending on what you want to choose as a time unit. The number of calls that arriving per time unit can be modeled as a Poisson distribution. And indeed, there is a very close connection with an exponential distribution. Namely, it turns out that if the number of incoming calls is modeled as Poisson distribution, then the intervals between the calls are exponential with the same parameter lambda. Lambda here for the Poisson distribution is the average. Poisson distribution is in general applied for the number of events in time, of number of objects in space. For example, when you have a highway in a sunny day, so all cars arrive there absolutely at random and there is no jam, then the number of cars on a 1 kilometer of highway can be modeled as Poisson, and indeed intervals between the cars will be then exponentially distributed. So this is the connection. So now I will show you some other connections which originate from binomial distribution, and in fact they were very important and maybe the first discovered in probability theory. So first of all, Poisson distribution turns out to be closely connected to binomial. In fact, if we take binomial distribution with very large n and very small p, then approximately binomial distribution becomes Poisson. For example, if you think about these lumps, if you have many lumps, say 1,000 of them, but each of them has very small probability to fail, say like 1%, then on average you will have 10 failed lumps, and it can be very well approximated with Poisson distribution with also the same average, the same lambda 10. So why is this? This is because, in fact, when we think about what real situation Poisson distribution models, we can also say that binomial model is applied there as well. Think about, again, call center. We have many customers, but each customer has very small probability to call in this particular time unit. So again, we have n independent customers, so n independent experiments, and very small probability. And then what we observe is that a number of calls is distributed by Poisson distribution, while we also could actually see it as a binomial distribution. So that's why we can intuitively explain why Poisson distribution is a limit of binomial. Probably a more important even limit and a fundamental limit is when just n goes to infinity without assuming anything about p. So when n goes to infinity, when the number of experiments becomes larger and larger, then actually binomial distribution can be approximated by a normal distribution. So why does that happen? That happens because normal distribution is not just only a model for some random variable which has some typical values I explained before, but normal distribution also arises from the central limit theorem, which has abbreviation CLT, central limit theorem. Central limit theorem tells us that if you have a lot of independent random variables and you sum them up together, then no matter what your random variables were, what distribution they had before, uniform or exponential, if they sum up together, then the sum will be approximately distributed as a normal distribution. So basically, large values and small values will compensate each other, and your sum will be likely concentrated around its average. So Binomial distribution also can be seen as such a sum, because in binomial distribution we deal with n independent experiments, and each experiment can be success or failure, and we count the number of successes. So each success is 1 and each failure is 0, and binomial distribution is in fact a sum of the 0, 1 variables, and therefore the central limit theorem is applied to this sum as well. And remember, experiments here are independent. So we can apply central limit theorem to the 0, 1 values, success or failure, and then we obtain the normal distribution in the limit. And that explains the normal approximation to binomial with large p. With large n, sorry, not large p, large n. So now, finally, people may ask, okay, well, we have binomial distributed by, approximated by Poisson, and binomial also approximated by binormal, but which one and where and when can we say that p is small? So, in fact, this all is logical because we also have this connection. When lambda becomes very large, then Poisson also can be approximated very well by the normal. So that's why this whole circle becomes closed, and all these connections, all these relations actually are closely related to each other, and they don't contradict each other. So in this picture, two things are important. First, which distribution models what? We have to always look at the real-time situation, the real-life situation, and see what model applies best in this situation. And that's why I always ask students to describe their model assumptions, why they apply this model and not another model. This is the first. Second are actually the errors, because mathematics is about establishing connections between different phenomena, describing phenomena in mathematical terms, and then when you describe them in mathematical terms, you discover connections between them. And that is exactly what these errors signify. Of course, there is a lot more to say about each of these distributions and about connections between them. However, in this video, I wanted to cover the information and the connections more or less that corresponds to a bachelor course in probability and statistics. I hope this story was clear. Thank you very much for watching this video.